something that they test on the AP test. However, I do like to go over it. Let C and L be real numbers. The function f has a limit L as x approaches C if, given any positive number epsilon, there is a positive number delta such that for all x, it just says for every delta there's a epsilon, every epsilon has a delta kind of thing. You take this class in college and they will teach this, they will go over this with you. For us, we do not have to have it. The main thing here that they're saying is that notation means that the values of f of x of the function f approach or equal L as the values of x approaches, but do not equal, not necessarily, C. Okay, figure 2.2 illustrates the fact that the existence of a limit as x approaches C never depends on how the function may or may not be defined at C. The function f has a limit 2 as x approaches 1, even though f is not defined at 1. That's the first one. The second one, the function g has a limit 2 as x approaches 1, even though g of 1 does not equal 2. And then the last one, the function h is the only one whose limit as x approaches 1 equals its value at x equals 1. And we have the graphs. And what they're referring to here is that basically claiming that f of 1 does not exist on this particular one. So we have the limit as x approaches 1 of f of x equals 2, but f at 1 is undefined. Anyways, we have an open circle, it's not defined. It has to have a closed dot there. The second one identifies the same thing. The limit as x approaches 1 of f of x is equal to 2, whether I'm coming from this direction or this direction. We're getting to the same point. However, f of 1 equals 1. This is okay. When we're doing limits, we're only concerned with the actual function. We are not concerned about a dot that's down here. The very, very last one, the limit as x approaches 1 of f of x equals 2, and then the limit as x, and f of 1 equals 2. There it is, that closed dot. Doesn't matter again which direction I'm coming from. When x is 1, I'm approaching 2 as a y value. Do not go crazy on these limits. You're only looking for a y value that may or may not be the value of the function. And that's what these two are trying to identify. It doesn't matter which direction I'm coming from, I get to the same spot. Again, same thing here, but I get to the same spot. And this one that has the dot on it. All three of these equations are actually the same. X squared minus 1 over x minus 1, if you factor this down and cleaned it up, is x plus 1. And so that's why all of the graphs look the same. And this one, they made it a piecewise function. This one's not defined at 1. They made it defined at 1. And this one, taking out, factoring this out and cleaning it up, forced the answer there. But again, remember limits. You are looking for a y value that may or may not be the value of the function. So these are a lot of different properties, and your homework does show this. So I'm not going to spend a lot of time on here. The sum and difference rule, these are the same. You can have like x squared plus 2x. You can do the limit of one and the limit of the other and then add them, and then you have the limit of the sum. Same with the difference. You can take these two, separate, do just the limit of f of x and just the limit of g of x, and then subtract them, and that will still give you the limit of between the two. The product rule, so you can find the limit of one times the limit of the other. So maybe you have like x squared minus 3 times x cubed plus 2 instead of figuring this all out together. You take one, get the limit, take the other one, get the limit, and then multiply them together, and that gives you the limit. Constant multiple, this just means that you have something like 5x squared, that you can find the limit of x squared and then multiply it by 5, and that would be the same as if you left it this way. A constant, the limit of a constant is whatever the constant is. So like if I can break these up and go, oh, the limit as x approaches 5 of 5 is 5. And then and then you can find this one here. Okay, quotient rule. The limit of as x approaches c of f of x over g of x is just L over m. Anyways, you can find the top, get the limit, do the bottom, take the limit. As long as the limit on the bottom one is not 0, this can be done. If it's 0, so if you have 5 over 0, this is not a limit. This is undefined or does not exist, however you want to write it. We don't do a lot with this one, the power rule idea, but this is self-explanatory. If I have something to a power, I find the limit of the value and then raise it to the power. And there's the other ones. The limit as x approaches c of k is k. This is that constant idea. The limit as x approaches c of 5 is just going to be 5. And this one here, if it's just x here, the limit as x approaches c of x is whatever the value of c is, because this is a plug and chug idea. Okay, I feel like I've missed one. Nope, got them all. So let's try one. I want the limit as x approaches c of this function. Now, one of the things we can do is break these up individually. The limit as x approaches c of 3x cubed plus the limit as x approaches c of 2x. But let's not get difficult. Let's just simply do it. Substitution, we're going to change all of our x's to c. So the limit as x approaches c of this function is 3c cubed plus 2c minus 9. That is that basic idea of limits, is just adding them in. Two more. Same thing, just put c in for x. So the limit as x approaches c of this function gives us c cubed plus 4c squared minus 3. I've got a fraction, I just have to make sure I don't get a 0 in here. So as long as, well, this is plus, so it doesn't matter. You'll never get 0 down here. So this one is going to be c to the 4th plus c squared minus 1 over c squared plus 5. These are the limits you're going to hope you get, where you plug in a value and you just get an answer, and you're done. Nothing, no big deal. The main thing I want to point out, you may or may not have seen a polynomial written out this way. If f of x equals a to the n, x to the n plus, and this is just meaning it's the next term, plus to the last term, is any polynomial function, and c is any real number, then the limit as x approaches c of f of x equals f of c. What are they saying? Polynomials, any and all polynomials. That is, you just plug it in, plug in the value, and you're done. Now, please, please, please keep in mind, a rational is not a polynomial. Anyways, a polynomial divided by a polynomial is not a polynomial. That is the main thing. It's a rational. So be careful with this guy. If f of x and g of x are polynomials and c is any real number, then the limit as x approaches c of f of x over g of x is f of c over g of c, provided that g of c does not equal 0. So you get a number, you can just plug these numbers in, you get a number. If this equals 0, undefined. If you get any other number, you're good, even if the top one's 0. So they want us to use a limit, theorem 2, which is the one that states that you can just do a plug and chug for polynomials. So the limit as x approaches 5 of this guy is going to be 4 times 5 squared minus 2 times 5 plus 6. 5 squared is 25, and 25 times 4 is 100, minus 10 plus 6. So we get 90 plus 6, or 96. So the limit as x approaches 5 of this function is 96. Do not overthink these. Another 2 examples. They gave a fraction one in here. They gave you a multiple one in here where you can pull them apart if you want. But I want the limit as x approaches 3 of this. So this is going to be 3 squared times 2 minus 3. So this is 9 times negative 1, or negative 9. Do make sure that you get into the habit of writing this. Don't just say, oh, the answer is negative 9. It's the limit as x approaches 3 of f of x equals. And this one is 2. So you get 2 squared plus 2 times 2 plus 4 over 2 plus 2. So this is really 4 times 3 because you're adding 4 up 3 times. So 12 over 4 or 3. So the limit as x approaches 2 of this function gives you 3. Now sometimes it's not going to be as easy as that. So evaluating limits, as with polynomials, limits of many familiar functions can be found by substitution at points where they are defined. This includes trig functions, exponential, logarithmic functions, and composites of these functions. So always try it first, I guess is the thing to say. Try it first. So I already gave you the graph over here. So looking at the graph, as x gets closer and closer to 0, you can see that your y value is 1. So we go, okay, the y value is 1. But that's because you have a graph to look at and you can do that. And yes, that's fine, you can do that. But we can also do this with algebraically. So this is going to be the limit as x approaches 0 of 1 plus sine of x over cosine of x. You need to know your unit circle for these. So this is going to give me 1 plus sine at 0 over cosine at 0. So it's 1 plus sine at 0 is 0, and cosine at 0 is 1, so I'm getting 1 over 1, or 1. So sometimes you have to work a little bit. Graphs always comes in handy when you're doing these. You can always use a graph. So let's try another one. So this is no different than what we've done before. Plug in 2. So 2 squared plus 5 times 2 plus 6 over 2 plus 2 gives us 4 plus 10 plus 6 over 4, which gives us 20 over 4, or 5. So this value here goes off to 5. So this was a fairly simple one. The question is, what do we do if we got more than that going on? Okay, this one here, the video is going a little bit longer than I wanted to, but we'll continue with it. It'll be about 20 minutes. Okay, so we just did this problem. What if x approaches negative 2 instead of 2? Can we still get the limit? Anyways, what if this guy here, not that guy, let me backtrack. What if this guy was x approached negative 2? Would we still be able to get the answer? Because now before, remember, when we put in 2, we got 20 on top. But this time if we do 2, we'll get 4 minus 10 plus 6 over negative 2 plus 2, which gives us 0 over 0. I know this isn't on your paper, but this is one to think about. Well, oh, wait a second, what do we do here? If you get 0 over 0, there's something algebraically you can do. In this case, factor. That just means that x plus 2 is a factor of this guy. That's all it means. So you factor this out, and you go, oh, okay. So I know that x plus 2 is a factor because Massardo just said x plus 2 is a factor. And that really, it's because you got 0 over 0. Getting 0 over 0 states that x plus 2 is a value up here. It's a solution for this guy up here. Negative 2 is. So now what do I have to multiply 2 by to get to 6? 3. So the other one's going to be x plus 3. Now you can see when I put in 2, I'm going to get 5. But when I put in negative 2, I get negative 2 plus 3, which is positive 1. Completely different answer, but we should expect that. We put a different number in. So this is one of the things to watch for. These are the things that we're going to be moving into. As such, find the limit. I want limit as x approaches 0 of 5 over x. Right, I cannot continue right now in this video, so we're going to start here on the next video. This is just where we'll begin. And I'll get this one going for you.